Okay, so for today's class, we're going to be going over some basics about the history of R and how R compares with SAS, as well as other programming languages. Then I'm going to give a brief introduction to some basic R concepts, and a lot of this course is going to be focused on data, and so a big component is getting your data into R. So I'm going to take a few slides to discuss that, and then talk about some programming rules and programming best practices, and then I'll talk a little bit about resources. Okay, so how did R come to pass? Well, R is a programming language for statistical computing, so it's used primarily by statisticians, data analysts, or data scientists. If you were wondering about the name, it was derived from the S language, so get it, S, then R. They weren't very creative, and it makes it very difficult to sometimes search for information about R, but S was developed by John Chambers at Bell Labs. R is a new project, which to us is most important because it's a free and open source programming language. You'll always be able to download it and use it for free, which is nice for people working in public health because oftentimes our budgets aren't very great. So this means you have the ability to do data analysis regardless of whether your company or your employer has SAS access. It was developed by two men, one at University of Auckland and the other at Genentech. And the thing about R is that it can really do almost anything, and one of the reasons for this is that users can create their own R packages and distribute them very easily. So the latest statistical methods will often have implementation in R. So I think it's updated a lot more frequently than some other languages. And I've put two websites here. One is the main R website for the R project, and the other is the Comprehensive R Archive Network, or CRAN. CRAN is where all the packages and R itself is stored. And so you'll visit that site, that's where you downloaded R, that's where you'll download packages that you might need. Okay, so in R, how does R function? Well, we create objects in R. And these objects can be many different things. An example might be a vector of heights. So if you've collected heights of all your study subjects, you could save that information as a vector in R. And then these objects can interact with other objects. So you might want to compare your vector of heights with a vector of ages and see how height and age might be correlated. And then in R, just like other programming languages, we write programs that apply methods to these objects. So this would allow us to do things like compute the mean height or to find the minimum age. This has a lot of utility because we can sort of conceptualize what we might want to do with our data maybe a little bit more easily than, say, SAS. R can be interactive. You can use it interactively, and I'll show that a little bit later. But that is an advantage over SAS, which is purely write the program, then execute the program. And R is easily customizable, so unlike other programs, we have a lot of control over how our figures look, how our tables look, and we can write our own functions to do pretty much whatever we want. So for SAS cannot be run interactively, for the most part, base SAS. SAS makes it really easy to look at your data, right? If you load your data set into R or into SAS, you can just click on it in the folders and open it up and scroll around, see what all variables you have, see what rows you have. That's a really nice feature. But it is difficult to create customized output. Have you ever tried to use ODS output to print things? It can be a real pain. You have to write a lot of lines of code. It can be difficult if you want to, say, do something like extract the mean age or the mean of all your variables, mean age, mean height, and put it in its own table. That's a lot easier to do in R versus SAS. SAS historically has been preferred to other languages because it can be more stable for complex models. That's less so the case now. The reason it used to be is that R was a pretty small community of users, and so if they're all submitting their own code, they may not get checked in the same way that SAS does, because SAS is this huge corporation. But the community of users in R has expanded dramatically in the past 5 to 10 years, and so really it's unlikely that these same issues are persisting now that there are so many people to sort of community check all of the code that gets submitted. And the worst thing that, or at least personally, I dislike about SAS is you need so much code to do something very simple. if you wanted to get the mean of a variable, you have to write at least 3 lines of code. You do proc mean, specify the data, specify the variable you want, run it, highlight the whole thing, send it to SAS, check the output. And then, of course, if you're me, you've forgotten to put a semicolon somewhere, and then you have to check your log, realize you forgot a semicolon, fix it, and run it again. R is a lot more concise. So to take a mean of a variable, we'd type mean of variable. It makes a lot of sense. Does anybody have any experience with other programming language or statistical languages like Stata, MATLAB, SPSS? Yeah? So we used a lot of Stata at Johns Hopkins instead of SAS. And Stata is really nice because it has really intuitive data cleaning. So if you have a really messy data, Stata would be what I would recommend to have to deal with that. It's much nicer than, I would even say, R. But the disadvantage of Stata is you can only have one data set open at a time. And for a lot of us, we're working on several data sets. Maybe you have data from one year and data from another year, and you're working on them simultaneously. And you can't do that in Stata at all, so that can be a little bit of a pain. For those of you who work or will work in genomics or brain imaging, MATLAB has been very popular because it can do matrix computations very fast. It's a very powerful language. And then SPSS, which is more used in the social sciences, it's very intuitive. It has drop-down menus, but it doesn't require programming, and it's very difficult to extend it. The nice thing about learning something like R is hopefully this class will teach you how to do sort of simple things to get you through a data analysis. But, in the next several years, if you decide that you want to start doing methods research, you can use what you've learned already and expand that to write your own programs, your own packages, etc. Okay, so now I'm going to take a minute to introduce you to R. So is most people able to download R in RStudio? Yeah? Okay. So if you have your computer open and you want to follow along, you're welcome to, but I'm going to show it on my computer here. So if you open up regular R, you're going to see something like this. So it's going to give you the version information. So now it's like off the screen. The version information and some disclaimers. And then at the very bottom, you'll see like a little caret and then the blinking cursor. This is what I mean by interactivity. So on that blinking cursor, I can type in R code. So let's just say I'm interested in a simple mathematical expression. Press enter and get the response from R. And so that means it's really nice to error check your code. Unlike SAS, where you have to write the whole block of code, then run it and see what happened, you can just write your code directly into R here and see if you created an error. So generally in R, just as a frame, if you see a response, such as this first one here, or you get nothing back, usually you've done something successful in R. When I mean successful, I mean R understood what you wanted. You may not have known that you wanted that thing. You may have gotten something back that you didn't intend, but you didn't cause R to create an error. R understood what you typed. If you create an error, like I did in the second line, it will say error and then give you a reason why. Those reasons why are not always helpful. If you ever get an error code that you don't understand, I recommend copy and pasting it into Google, because someone likely has already done that and asked the question and hopefully has responded. This one is probably not very helpful. Unexpected string constant in 5 something something, but really what it meant is I had a typo. And most of your errors probably will be typos. So just double check when you receive the error. So this is the interactivity in R, but just like SAS, we really want to be writing most of our code in an editor. So this is what the R editor looks like. You can get to it by either clicking on, there's like usually a white page, or doing File, New Document. And then just like SAS, we would write our code here in the same way that we did in the terminal, in the console itself. And then we can send that code to R using the shortcut Command-Enter for a Mac, or I believe it's Control-R for a PC. Although we were not going to be working in base R for the most part, so this is really more FYI. But if I do that, you see it goes to R, and now I've run my code successfully. But as I said, we're not going to be using primarily the base R, but this just is a nice way of introducing you to RStudio. Because RStudio has a lot more windows. It's a little bit overwhelming. But you'll notice that the top 2 windows that I have open, so the one on the far right here and the one on the left, are exactly the same 2 windows we saw in regular R. You'll notice we have the version, we have some information, and then we have our cursor. And just like before, we can either type in code here and get a result, or type in code here. Although I believe on our studio, on a PC, the command to enter code from the editor to R in our studio is Control-Enter and not Control-R. For a Mac, it's the same in both. Any questions so far? So we'll come back to all the other windows. They do useful things, but these are the main two that you'll need. And just to reiterate, for those of you who aren't familiar with interactivity as a thing, you really want to be using it more for debugging. So seeing if you have errors in your code, or if you want to do some quick math. You're like, I don't know what, my average grade in this class is. Let me type out my grades and divide by 100 and see what it is. Something that you don't want to save for later. You just you're curious. You never want to do something like copy and paste from the console to another document. You really want to be writing your code in your editor. That's the code you want to keep, and then executing it from the editor to R. And when you save this editor file, it will become a .r file, and that's just an R code file. And that's what you'll need to submit, at least for the first 3 homeworks. That's all you'll need to submit. So you won't need to submit any of the output, just the code that creates that output. Any questions so far? Okay, great. Let's go back here. Okay. So when you open R opens the console, which is where you type in code interactively. What R opens is actually is running R in the background. What RStudio opens, R is running in the background while you're running RStudio. So they're not 2 separate programs. That's why you needed to have both downloaded. So for example, RStudio is just sort of a way of running R and seeing it differently. It has a nicer layout and additional features. So one thing that RStudio brought to the table that R didn't have is that in R, the way it comes naturally, there's no easy way to look at your data. So unlike SAS, where you can just open up your data set and scroll around, R didn't have that, and that's kind of a pain for people working with data. But in RStudio, we do have that capability. So that's why we prefer RStudio. Another reason is it runs pretty similarly between Mac and Windows, other than the fact that Windows computers don't have the command key. So the entering code is different. But other than that, it looks the same. Whereas on a Windows computer, at least last time I used based on a Windows computer, it looked a little bit different. So you'll notice that, like I said before, R does update very frequently. Current version is R version 3.1.2, which has codename Pumpkin Helmet. I will say it's not my favorite one. My favorite one was actually the version that was shown in the R download video. 3.0.2 was Warm Puppy, which is just, I don't know how they came up with that name. It's either really cute or really creepy. I'm not sure which. But so I always get excited when you download a new R version to see what the code name is going to be. Okay, so just talking a little bit about basics in R code. As I said before, I used RStudio to create these slides, which is nice because I get the code in there. Not so nice for you because it's difficult to print. But to orient yourself, the first box, I don't know if you can tell in there, it's a little bit darker. And that's code that I would write in either my editor or in the console. And then the following line where it says 1.8, that's what R would return. And so you'll see that throughout this lecture, there'll be a sequence of these boxes that will show code you can write and what R would respond with. And so we can do simple mathematical expressions, can make them a little bit more complex using division and parentheses, just like you would in like a graphing calculator. So R can be your new graphing calculator if you still have one of the TI-83s from ages ago. Okay, so the first thing I think that you need to know to use R is how to save information. So great, R can do computation, but what if I want to remember what this expression is later? Or if I compute my grade and I want to remember that later, or determine what my grade will be in the future. We want to save those objects, and the way we can do that is using assignment operators. And there are actually 2 assignment operators in R. The first one is the caret followed by a dash. And what this says is I want to assign the value 5 to the object that I just named name of object. And this name can be pretty arbitrary. We'll discuss a little bit more about naming rules later. And then if I print that object, if I want to show what that object has in it. I type print, name of object, and then you see that it's 5. I can also just use one equal sign. So I could print name my object, name of object 2, assign that also to 5, and you see that the result is the same. In general, the R community, the old community, I guess, prefers the caret dash for programming reasons that I don't quite agree with. I use that because that's how I learned it. The proponents of using the equal sign say it's so much easier. You don't have to use shift. You don't have to use 2 characters. Do whichever you prefer, but just a little bit of our history. So on the right-hand side of assigning these objects, you can really put anything. So you could put your mathematical expression on the right side of the assignment operator. And then just to highlight something that is important, printing that object is the same thing as just writing it out. So if you want to bypass the print, you don't need that there. You can just write the object and R will automatically print it for you. So it's a little bit of a shortcut. You can also create new objects as functions of other objects. So here we have name of object, which was 5, name of sum, which was 5 plus 3, and now we've created a new object that has the value 13. Objects can be reassigned, so the same name can be reassigned to a different value. This is nice if you want to discard the value that you first assigned something. It can be dangerous because if you have a data set that you call dataset and then you reassign that data set to something else, you've now lost your first data set. So be careful. R will not give you a warning or tell you, hey, did you want to overwrite that? So it's just important to be aware what you already have created and know if you're overwriting something. So we've only been dealing with number valued R objects so far, but there are many different types of what we call data classes in R. You can always check to see what class an object is by using the class function. So we just type class and then in parentheses whatever we want to take the class of. So if we take class of name of object, which again was just the value 5, we see that it's numeric. Probably not surprising. But just like in SAS, we also frequently deal with objects that are not numeric, such as character values. In an epidemiology setting, these could be things like race or sex that don't have number codes. And we can create those in R by just putting quotations around whatever we want to make a character or string valued object. And you'll notice when R prints it prints it with quotations around the object so that we know it's a string. And if we check the class of it, it's going to be a character. Yeah?
These variables that we're creating, like name of object, name of sum, are they case sensitive?
Yes, they are, and I'll cover that a little bit more later. We can create vectors by combining objects together. So the C function, it's a very short function, stands for combine. And within the parentheses, we can put the objects we want in our vector separated by commas. One thing you'll notice is that if I create this vector using the C function, when R prints it, it doesn't print those commas. It just puts spaces in between the objects. Again, since all of the elements in this vector are numeric, the class of the vector is numeric, and we can find other attributes of the vector by applying different functions. As an example, we could see the length of the vector is 4. We can also create vectors of strings. It's really no different, except that when we take the class of the string vector, it tells us it's a class character. So what happens if we mix data classes? So this can happen when, for example, if you are doing a survey and you're recording people's income, self-reported income, and people are saying, oh, $50,000, $100,000, $20,000 a year, and then someone says, millions and millions of dollars, and your data entry person types millions and millions of dollars. Well, everything else in your vector is going to be a number except for that one thing. So what happens when you have a vector like that, and I'm pretty sure SAS performs the same way, is that when you print the vector, you'll notice that that last number now has quotations around it. So R no longer understands that as a number. It's now converted it to a string variable. So R will do its best with a vector to convert everything to numbers, but it doesn't understand how to convert the word intro to a number. So the whole thing will convert to a character variable. So that's important to remember when you're doing data cleaning, because if you have something like income, you want to make sure you're eliminating those cases that are problematic, that will inhibit your ability to do data analysis on that variable. We also have factors in R. Factors are very important in data analysis as well. I'm sure you have encountered them in SAS. But let's suppose we have a vector of grades, so we have grades A through F. And if we take the class of grades, it's a character. But really, character variables are meant for things that can take on an infinite number of possibilities. But if at the end of this class I gave you a grade of J, you would be like, I don't understand what that is. There's only A, B, C, D, and F. There's no other grades that I could possibly give you, aside from minus and pluses. So really, we want to say that there are only a limited number of levels that this variable can take on, and we can use the factor function in R to do that. So we take factor of this variable. What R does is it says, all right, let's look at all the individual unique items in this vector, and those we will call the levels. So you'll notice that the levels are A, B, C, D, and F, as we would hope. And then notice it cut off at the bottom a little bit, but it says class of factor grades is, not surprising, a factor. And so you might be wondering at this point, well, why does class matter? Well, it matters for us interpreting information, as I explained in that income example, but in the context of R, it matters because functions behave differently depending on the data class. So for example, we've already seen this. When we printed grades, before we changed it to a factor, we just got the list of grades with quotations around all of the elements. When we printed the factor grades variable, we got all of the items in our vector, but then we also got the information about the levels. So it gives a little bit different information depending on the class of our object. And this also makes sense in the context of applying statistical functions to things. It doesn't make sense to talk about the mean of a character vector. What would you even call that if you said, what's the mean race? You can talk about maybe the most frequent category, but taking the mean of a character vector is really meaningless. And there are other classes in R that we will be discussing in the next class, including matrices and data frames, which are critical when we're dealing with data analyses, as well as things like lists and dates. There are also classes for R output. So there are many, many different R classes. You're not expected to learn them all. You will get comfortable with the ones that you deal with most frequently. But the advantage to this sort of setup is that we can assign a class to, say, linear model output. In R, linear model has a class LM. And what that means is that when we print an LM or we plot an LM, it has certain behavior that we like. So it's going to print things that we want to see. It's going to plot things that we want to see, instead of it being default across all sorts of different classes. And you can create your own classes, actually, in R, but that's beyond the scope of this class. So an important part of data analysis is being able to select elements from these R objects. This is relevant because we might want to restrict our data set to only people who earn less than $100,000 per year, or only look at males. And so looking at this in a smaller setting, we have our vector string that we created earlier, and we can use bracket notation to subset portions of that vector. And what I mean is that you put a beginning and end bracket after the R object, and then you, inside the brackets, indicate which element you want to select. And these are based on the number. So here, vector string 1 selects the first element in that vector. Vector string 5 selects the fifth one. Any questions so far? So we've already seen a lot of our functions, but just to formalize how they behave, generally we call a function by writing the name of the function, and then in parentheses the R object that we want to apply that function to, generally. So for example, if we wanted to take the mean of our vector 1, we would take mean of vector 1 and get back the mean. It gets a little bit more complicated because we can add arguments to our functions. And this is helpful because instead of having to do some fancy rearranging of our vector 1 in order to create the trimmed mean, the mean function itself has an argument called trim that can compute the trimmed mean for us. So if you remember the trimmed mean, where the trim is 0.25, says I'm going to remove everything below the 25th percentile and above the 75th percentile. And so when I compute the trimmed mean here, it's deleting the 6 and the 2 and computing the mean of 3 and 4, which will be 3.5 as opposed to 3.75. And then there are plenty of other functions. I'm going to highlight the log function because that tends to be very common in both statistics and epidemiology. As a heads up, the log here, we're talking about natural log. I know for anyone with engineering background, they always think log base 10, but in R it behaves like statisticians do, where we don't use ln for log. So some other R functions, we've seen length, which tells us how many elements are in our R object. We can also compute the median. If you take the summary of a numeric vector, we get a lot of nice information. It gives us the minimum, first quartile, median, mean, third quartile, and maximum. Another function that will be useful later on in this class is the ls function. You'll notice it behaves a little bit differently than other functions because it doesn't take an argument, or at least it doesn't have to take an argument. And so if you type ls with nothing in the parentheses, what you get back is everything that you created in your R session. So you'll notice we started creating vector 1, we created name of new. All of these things are things that we created in this R session. And that can be useful if you forget what you called something, or if you want to see if you're going to be overwriting something you've already created. So I talked a little bit about this earlier, but I'm going to formalize what I mean when I talk about R packages. So R is huge, has a huge amount of functions, information, and these are all compiled and stored in packages for the most part. Some packages come preloaded with R, so when you downloaded R and when you open it, there are some packages that you don't need to call in order to use their functions. So for example, mean, print, and length all come in the base package. Median and LM come in the stats package. The package datasets is pretty nice. It has a bunch of different datasets that you can use to play around with or to see in R. And the graphics package allows us to do plotting. But there would be a problem if R decided I'm going to just preload all of the packages that exist, because there are hundreds and hundreds of them. And so that would be a lot of memory that R would eat up and probably crash our computer. And so what you can do is our CRAN has all of these packages stored on, all of these packages are stored on CRAN, and when you want them, you would install them and then load them to use in your R session. So you can think about installing a package as sort of like downloading it off the internet. So just like you downloaded R, you download Microsoft Office, you install the package, and you can do this from R by typing the command, the function, install.packages, and then specifying the package you want to install. And then this seems to have slid up a little bit. And then to load the package, we use the command library. And you can think about that as once you've already installed the package, you need to load it into memory. So you only need to install it once, but every new R session, you would need to call library so that you can use those functions in those packages. That's not going to be super useful to us in today's lab, but you'll see it in future labs when we start getting into advanced graphics. And for those of you who are working with data sets, maybe in SAS or Excel, you'll see that you need external packages to read in those types of data. Okay, so is everybody familiar with the concept of a working directory? Is that a familiar term for people? No? Okay, so does everybody remember setting their lib name in SAS? Okay, that's familiar. So this is sort of the same idea. It's a little bit more general to programming. So this concept will, if you do more programming outside of R, will come back. So the working directory is where R looks for data, as well as where R saves data, figures, etc. And so if we want to, say, load in a data set, we need to tell R where R can find that data set. And one way of doing that is to set the working directory. The way I always do this in my own practice is to first find out where my working directory is. This gives a sense of the file path for your computer. And so if you're using your laptop now, but you go to the computer lab later, you might not be familiar with how the file path is set up there. So typing in get wd, again, no arguments inside, will tell you where R is currently looking. And then you can revise that path name to then set your working directory using setwd to a different folder. So for example, if this is the folder I'm currently looking at, but I don't want to be in this folder, I just want to be in my Dropbox folder, I can then type the command set working directory and then put my file path in here. Does that make sense? Okay. So I know I'm a Mac user, so this is like Mac specific, and then hopefully I'll help those of you who are on Windows as well. For Windows, it's going to look something like this. Excuse me. Where you're going to need to specify C unless you're working in a different directory like the external drive. But again, it will be users / your username. A nice way of getting to your home directory, a shortcut, is using a ~/. So if you ever want to reset just to your home directory, you can do that. And so my home directory is users /crawl. If you're a Windows user, it'll probably be C-users - whatever your computer's name is. Okay. So let's talk a little bit about getting data into R. I think this is a critical first step in any data analysis because I can't tell you how many times I've gotten frustrated trying to get data into one program or another, and it sort of holds up your whole analysis, right? Because until you can see that data, you can't really start. And R is nice because it actually has pretty easy commands for reading in data from a bunch of different sources. And again, it's a lot more concise than SAS. Sorry, I don't mean to be hating on SAS. I actually use SAS fairly frequently. It's just that I think my first love will always be R. So R does have its own data files. So if you ever see a data file with the extension .rdata or .rda, that's an R data file. And those are the easiest to load into R. Mostly because by default, you can just double-click them and R will open them. You'll have to specify if you want RStudio to open them versus R usually, but so that's a nice, easy way of getting data into R. So as an example, so this is our course website. I don't know if you visited it recently. I did add a calendar, so hopefully you'll remember to come to class. If you go to lectures, I've put all the data sets that we're going to try and read into R up here. And so if I click this, this is the Google flu data that I'll introduce in a second. If I show it, double click it, and now it actually loaded into R. So that's the easy way. It gives you the command after you double click it, so that's nice. Let's talk about the data, and then I'll talk a little bit more about our data sets in a minute. So the data that we're going to be dealing with in the rest of the lecture, as well as in the lab today, and in a few subsequent weeks, is Google Flu Trends data. Have you guys heard about this data set? Yeah. It made the news a lot in the past couple of years. So what Google decided to do is they said, okay, well, people tend to search for the maladies they think they have. So if you're not feeling too great, you've been in bed for a few days, you're feeling weak, you know, respiratory problems, you might start searching for flu symptoms or flu remedies. What drug should I take? What should I eat? Google said, well, maybe we can use this information to predict flu activity before the CDC gets that information, because CDC relies on public health organizations to collect the information, and those often rely on doctors. So you might imagine your trajectory: you get sick, you search for flu symptoms, you search for flu remedies, you're still sick, you finally go to the doctor. If we can get that first point when you're searching before you've actually gone to the doctor, we're able to determine when there's increases in flu activity before the CDC, by its traditional methods, do. I will caveat that by saying that a recent science paper came out with a bunch of problems associated with this method, and I feel like as epidemiologists we can commiserate because they sort of believe in the big data phenomenon, right? If I collect enough data about Google searches, I should be able to predict this. But the problem is we know that correlation is not causation, and so a lot of the factors that they identified as being associated with flu season were like searching for basketball scores or the Super Bowl, because those things are correlated with the flu season because they happen in the winter. So they missed a big peaks, I believe, in the flu season 2 years ago, and are not always super accurate, although it's a fun data set to play with. You can read about their methods in their Nature paper that they submitted. And I've sort of cut down the data set to include only 4 variables of interest to those of us at Emory. So we're going to be looking at the whole United States, Georgia, Atlanta, and then the HHS Region 4, which is the southeastern U.S. states. Okay, so let's get this data into R. As I said, if you have a data set that has .r data, you can frequently double-click it and get the command. So when I double-clicked the data before, if I can move this up a little bit, you'll see that I got the command for actually loading this data by double-clicking it. So that's a nice way of reminding yourself how to get R data into R, but you can type that command directly. So you'll notice that here it had typed out the full path because I wasn't currently in that working directory. But let's suppose the data is in the directory we're currently in. We can just type load and then in parentheses the data file including the extension. You notice this is one of the things that is both lovely and frustrating about R. You type load and nothing happens. There was R didn't say anything. So as I said, if you did that, that means that R understood your command and did something. It may not have been the thing you wanted, but it did something. But if I look at what's in my current workspace using my ls function, you see I now have this object flu that didn't previously exist. And so I can use a function called head, which is very useful when dealing with data sets. It gives you the first 6 rows and all the columns of your data. So you can see that I have four variables, date, United States, Georgia, Atlanta, and HHS Region 4, corresponding to the estimated flu activity for those 4 regions and the corresponding date. Now if I use my class function, I can see that this is a new thing. This is a data frame, and we'll be using data frames frequently in R. Okay, so here's an example using a CSV file or a comma-separated values file. So CSV files are pretty common cross-platform. You may have dealt with them in SAS before. If we look at what a CSV file looks like in, for me, TextEdit, you could look at it in Notepad using a Windows computer, you'll notice that all the entries in the dataset are separated by commas, hence comma-separated values. So we can use the command read.csv to read that file. If I just type the read.csv in the parentheses, it will just print the data out. So let's try this. Actually, set working directory. It's always one of the scariest things typing in front of people, because if you mess up anything. Okay, so this is what happens. So this isn't too bad of a problem because this data set isn't huge, but imagine if you have tens of thousands and thousands of rows. You don't want to just print all that out. You want to save that output to an object. So that's why we have to, when you have R data files, R is smart enough not to just print everything out, but when you have data files like CSV files, you need to assign them to an object. So we're going to call that object flu. So when I do that, and now I take the head of flu, you see that I have the same data set that I loaded before. The second argument I've included here is completely optional. You don't need it there. You could do read.csv without it. However, the way R's default works is that it automatically converts any strings to factor variables. And what that means is that if you had a typo in your data set, which occurs frequently in real-life data, it will be very difficult to fix that typo. If you read it in as strings as factors equals false, you can fix problems. So unless you're 100% sure your data set is clean, I would set strings as factors equals false. It's just good practice. You can always convert it to a factor later. That's a much easier thing to do. And then if we see the class again is a data frame. Oh, I keep doing that. All right, we can also get Excel data into R. Probably the easiest way of doing that is opening your Excel data file, which is hopefully open somewhere. Where'd it go? There we go. So this is the data in Excel. Of course, you can always do File, Save As. Maybe. My Excel keeps crashing. It does not perform well on a Mac. And if you click the format here, you'll notice that one of the top options is to save it as a CSV. So that's one way of getting an Excel file into R, save it as a CSV, and then use the read.csv as we saw earlier. Another way is to use to read it into R directly, and you can do that using the Excel Connect package. So this is our first venture into packages beyond those base loaded with R. So you would need to install that package first using the install.packages command, and then once you've installed it, call the library. And so the way that this function works is it loads workbooks. So if you are familiar with Excel, Excel files are often called workbooks. And so first we're going to load our workbook, which is Google Flu, and then it has the extension .xls or .xlsx. If we look at the class of that workbook, it's a workbook. Well, we don't want a workbook, we want a data frame, because that's how we interact with data easily in R. The reason that this function does that is, if you remember the way Excel works, is oftentimes we have a bunch of different tabs at the bottom. So you can have multiple data sets stored in one Excel workbook, right? I could have different tabs for different years, for example. And so you need to tell R which tab you want to read in. So the way we do that is the read worksheet. So once we've loaded in the workbook, we say, okay, R, read that workbook and select the first sheet. And then once we do that, it looks just like we had before. And you're not expected to memorize any of these functions. This, I hope, will be like your reference sheet going forward for any class or project that you're working on, that you can reference this to determine how to get your data into R. And then last, we're going to talk about getting SAS data into R, which you have different options. There are 3 different options I'm going to go through. I would recommend 1 or 2 for reasons I'll get to in a minute. So just like in Excel, we can first save it as we can save our SAS data set, which generally has the extension SAS7bdat, as a CSV file. So I've just given you some example SAS code here. If you're familiar with SAS, it's just the standard proc export. And then once we've exported that SAS data file as a CSV, we can use our read.csv function. The second option is to save your SAS data as an export-transport file. That's nice because it's easy to get into SAS and it's also easy to read from R. And here's just some sample code here. If you're not comfortable with this, don't feel obligated to learn it. It's just, again, for your own reference. Once we save our SAS data as an export file, we can use this function, sasexport.get, from the hmits package. And the nice thing about that is it's a SAS data file, but R can read it and gives us a nice output. The last way is that there is an R function that can read SAS7bdat files directly. I have not had much luck with it, mostly because, well, I'm a Mac user and I can't run SAS on my computer, and that function requires SAS. You have to have SAS on your computer, which means you have to have a Windows computer. I also find that it tends to give you really unhelpful errors, so it can just be a hard function to troubleshoot, but it's here just in case you're interested. There are other functions to get data into R. You'll be dealing with one of them during the lab. And it really just depends on what kind of data file you have, though I hope I've covered the most common. So we're going to talk just for a minute about rules about programming. The first is to always, always, always comment your code. You should be familiar with this as SAS users. You will be graded on this. If you submit code for a homework assignment or for your project that is not commented, you will lose points. You can create comments in R by putting a £sign before the line that you want to comment out. And then just provide some descriptive of what you're doing. And I saw this quote recently that I thought was at least spoke to me about code commenting, and it says, your closest collaborator is you 6 months ago, but you don't reply to email. So you don't want to be in the scenario 6 months from now where you're like, oh my god, what is this R code? I have no idea what it does. So make sure you're keeping your future self happy. The other thing is to use appropriate spacing. So you'll notice that in this expression, I've put spaces before and after the assignment operator and then after all of the commas. That's not necessary. So I could remove all those spaces from that expression and R would be fine. But it makes it really difficult for other people to read, so it's expected in this class that you'll make your code easy for the You don't want to make your TA mad. Like, you don't want to have your code difficult to read, even if it's right. Maybe Anran will just be taking points off left and right. I don't think she'll do that. She's very nice. Your lines of code should not exceed 80 characters wide. It becomes very difficult to read if you let your code wrap. So at the end of 80 characters, you put a return line and then 2 spaces. The nice thing about using RStudio, if I can find it, is that RStudio actually has a line width counter. So you'll notice this first number, can you see it on there? This first number here is the horizontal line you're on, and the second number is the vertical line. So if I keep typing, you'll see that this number increases. So if you notice that your line width is exceeding 80 characters, please shorten it. A nice way of doing that, I often do, is to make your window width 80 characters wide, and then I'll remind you to return down at the next line. Okay, naming conventions. Finally, Ishwar's question before. You can use capitalization and camel case for your names of your objects. I don't recommend it because it makes it more difficult to type and remember, but that does mean that if you create a vector that's capitalized vector 1, that will be different than a lowercase vector 1. So as an example, back down here, if I create vector 1 equals 5 and I say, okay, tell me what vector 1 is, it doesn't recognize it. There is no vector 1. So I recommend just always using lowercase. You can use underscores to separate words in names. So if you put an underscore to make it a little bit more readable, that's fine. Don't overwrite existing R functions or objects. That's very difficult for you because you're just learning R. So you might be saying to yourself, well, I don't know what the existing functions are, and since R doesn't mind if I rewrite things, it's kind of a problem. For now, I'll say don't overwrite C or T. Nothing is set in stone, so if you do something you didn't need to, you can always close R and start over again. And it's not going to be dramatically tragic, but I would recommend not doing that. If you want to learn a little bit more about how to write R in a nice way, stylistically, I've posted 2 style guides here. I would recommend Hadley Wickham's. He works for RStudio and is a great contributor to R, and so I feel like his advice is always useful and good. And then just to talk about resources for a minute, the biggest one that you'll be using today is looking through the R help files, and you can access those by using the question mark followed by whatever function you want to look the help file for. Sorry. So if I wanted to look at the help file for mean, I could type in my console, question mark mean, and you'll notice that RStudio pulls up a window corresponding to the help page for mean. So I'm just going to take a minute to go through what this looks like. The function name is going to be in the upper left-hand corner, followed by, in brackets, the corresponding package. So this is in the base package. Then you have just the more descriptive name, followed by a description of what the function does. The 3 following sections are going to be the most important as you're learning R. The usage tells you how you're going to write your R command. So here you can look at how we wrote our mean command when we were taking the mean of our numeric vector. We typed mean of x, followed by trim equals, and then we specified 0.25. To understand a little bit more about what these arguments are, you can look in the arguments section. So here we see that that trim is the fraction from 0 to 0.5, designating how much of a trimmed mean you would like. You'll notice that in the usage section, trim has a default value, and that's where you see the single equal sign. So if I don't specify what I want trim to be, it's going to default to 0, and if trim is 0, that's just your standard mean. Anything that doesn't have an equal sign, you have to give an argument for. So if I just try and take mean of nothing, it's going to say, I don't know how to take mean of nothing. Doesn't make any sense. The value section will give you what output you should expect. So here it's just saying when trim is 0, we're going to get the arithmetic mean. Great. The following sections are of varying use depending on the function you're looking at. There's some references. There's like a see also section, which is like, if you are interested in mean, here are some other functions you might be interested in, which actually can be quite important if you can't quite remember the function you want. And then some examples. Another way of getting to help pages that I find useful is using the function help.search. And what this is useful for is if you don't remember the name of the function. So say you knew that the function you wanted had the word mean in it, but it wasn't the mean function. You can look here and see all of the functions in R that have mean in them. And thankfully, the function mean has mean in it. So if we click on that, we get back to the page for the help file. So that will get you through all of the help pages in R, but oftentimes the help pages are known to not be super helpful, particularly if it's a confusing function. You may want to visit some of the other resources I've put on the website. If you ever get an error that you're not sure how to deal with, sometimes Googling it can help. There's also an rseek web page that searches only R-like documentation, so it's not going to be a broad search as searching in Google. There's also pages like Stack Overflow, and UCLA maintains a nice statistics page. And then I also have my resources page here. Okay, so that's it for